So we made it kind of the end of chapter 4, and we've learned quite a bit of stuff, right? So we've learned how to predict the shapes of molecules, if bonds are polar or not polar, if using electronegativity, and then using if bonds are polar or not polar if a molecule is polar. And now we're going to look at this, the interaction between molecules. So intermolecular forces, inter means between. So this is going to be forces that occur between molecules. So if I've got, let's say, 2 ethanol molecules, it's the forces that occur between them. And that's going to be based on if they're polar or not polar. Okay. So there's 3 basically intermolecular forces we're going to look at. There's going to be these things called dispersion forces, which are also called London forces. And those are going to be the forces that occur between all molecules. But if I've got nonpolar molecules, it's the only forces that hold nonpolar molecules together. Okay? But dispersion forces occur with all molecules. Dipole-dipole forces are going to occur between molecules that are polar, that have that we've determined to be polar from how we do that. And the final one are hydrogen bonding forces. And hydrogen bonding forces are just really strong dipole-dipole forces. And we'll look at what that means. Okay, got a little table of how this works, and we'll come back to this. But basically, if there are no polar molecules, then the only forces that are active on those molecules is dispersion forces. If there are polar molecules, then I've got dispersion forces plus another one. Are there OH bonds or NH bonds around? And if there's not, it's just dipole-dipole forces. And then if there are NH or OH bonds, then I have all 3 of these. I have hydrogen bonding, dipole-dipole forces, and dispersion forces. So let's look on dispersion forces real quick. All right, so we've seen that polar molecules or polar bonds occur when electrons are shifted, when electrons are pulled towards one atom away from the other. We get a negative and a positive end, and that makes a polar system. And polar systems are attracted to other polar systems because the negative end of one molecule is attracted to the positive end of the other molecule. Okay, so if I don't have a polar molecule, that means everything is nonpolar. So how are the molecules attracted to each other if they're not? If the polar ends, the positive and negative end, aren't doing this? Well, what happens is that ultimately there are poles, but they're instantaneous or temporary. And if you think, what you can think about this as the electrons are around the molecules, right? And they're moving, and they're constantly moving. And there are going to be times when they're just perfectly equally distributed around the molecule, and it's overall, everything's balanced. All the electrons are balanced. But most of the time what happens as the electrons move around, they're not entirely balanced, and it causes maybe there are just a little bit more electrons near one end of the molecule versus the other. And when that happens, it causes a temporary dipole because there's more electrons on one end than the other, so one end is slightly positive and one end is slightly negative. But it goes away really quickly because the electrons are always moving, and it may move so it goes the other way. But these really quick instantaneous dipoles, like here, affect everything around it instantaneously. Because electrons are so small, they can respond to things instantaneously. So if this molecule in the middle all of a sudden gets an instantaneous or temporary dipole, because the electrons aren't quite perfectly evenly distributed, these molecules around are going to feel that. So if this end of the molecule is positive, what's going to happen is in this molecule is the electrons are going to get pulled that way. They're negative, they're attracted to positive charges. And I'll get that molecule will look like that real briefly, real shortly. And the molecule, let's say, is here. It kind of sees a negative charge. That means the electrons are going to go the opposite way because they're repelled by negative charges. And I'm going to get a positive end and a negative end. Okay, so this just happens all the time in molecules. The electrons are shifting a little bit. When they shift a bit, they're not equally distributed. It causes a slight positive end and a slight negative end, and it's just always happening. And that's what dispersion forces are. It's not permanent dipoles. It's not like we've got electronegativity differences that cause the electrons to spend more time around one atom than the other. That's not what this is. This is because the electrons are moving a little bit. They don't stay equally distributed. Therefore, we get a slight positive and a slight negative. Okay, but that's what's holding all these guys together. So if I've got like octane is all carbons and hydrogens. It's nonpolar, but octane becomes a liquid, right? When it's a gas, it becomes a liquid. At room temperature, octane is a liquid. That means the molecules are attracted to each other. And it's this type of force that attracts octane molecules to each other because octane is not polar. All right. Because these are temporary, these are typically considered the weakest type of intermolecular forces. However, if you get really long nonpolar molecules, these forces can be pretty strong. And again, dispersion forces occur between all molecules, but if it's not polar, if the molecules aren't polar, these are the only forces that will affect nonpolar molecules, or cause nonpolar molecules to be attracted to each other. Okay. Our second force is dipole-dipole forces. So if we have two polar molecules, or one polar molecule, but there's two of them, so two polar molecules, the molecules are attracted to each other because one end of the molecule is positive and one end of the molecule is negative. So the positive end of one attracts the negative end of the other, and so on. So if we've got this kind of this picture of, again, this is formaldehyde. We've got this carbon-oxygen bond, which is polar because the electrons are pulled more towards the oxygen. Oxygen is more electronegative than carbon. When that happens, we get an end of the molecule that's got more negative charge and an end of a molecule that's got more positive charge. And we depict it simply in kind of like one of these ovals where one end is positive, one end is negative, although this should be the negative end and this should be the positive end if we're going by what we've been doing here. So if we put a collection of molecules together, we can see if this is a liquid, they're always moving around, but as they move around, there are going to be some preferred orientations, right? So if this molecule is next to this molecule, and this is the negative end, this molecule is going to try to rotate to put its positive end with the negative end, and so on. And you can see if you look at these, they're kind of all set up that way, where the ones next to it, it's kind of opposite direction, so that the positive end of one molecule can interact with the negative end of the other molecule. Again, if this is a liquid, they're just moving around, but when they get into those, they spend more time in favorable interactions than unfavorable interactions. Okay, this is kind of the easier view. You can more clearly see what's going on, maybe not. But that's kind of how we depict these processes. So molecules that are polar have both dipole-dipole forces and dispersion forces between them. And then the last one is hydrogen bonding forces. So hydrogen bonding is just a really strong form of dipole-dipole interaction. And hydrogen bonding occurs if the molecule has one or more of these type of bonds: a hydrogen-fluorine bond, a hydrogen-oxygen bond, or a hydrogen-nitrogen bond. And what we've got here is kind of a depiction of water. So water is H2O, so hydrogen, oxygen, hydrogen. So it's got the hydrogen-oxygen bonds. So in water, what happens is the oxygen is more electronegative than the hydrogens. So the electrons are pulled, the bonding electrons are pulled towards the oxygen, which makes the oxygen slightly negative. And it makes both hydrogens slightly positive. So when a water molecule interacts with another water molecule, the hydrogen from one molecule is going to want to interact with the oxygen from the other molecule, because one is slightly positive and one is slightly negative. And this happens. So when I bring a bunch of water molecules together, as they're moving around, they try to orient so that hydrogens are interacting with the oxygens of the other atoms, and so on, in forming these things called hydrogen bonds. Now, don't be fooled. Hydrogen bonding isn't as strong as covalent bonding. Okay, it's not a permanent thing like covalent bonding is. It's a temporary thing, but it's a strong interaction. If we want to take a step further, if we want to take a step further and see how this is applied in biological systems, so DNA strands, remember DNA is doubly stranded. It's got two strands that hook together, meet together, and what happens is when they meet, so when we're putting these together, we've got these four. So we have these base pairs that are labeled as G, C, A, and T, right? And we can see them here, where G and C interact favorably and A and T interact favorably. And what actually happens is there's a hydrogen bond that occurs between G and C, and there's a hydrogen bond that occurs between A and T. So when the single strands line up and they have their matching partner next to them, there's this hydrogen bonding network that occurs. Okay, all the way down for every base pair down the helix. When DNA has to separate to be replicated, the hydrogen bonding network breaks, kind of like a zipper, starts at one end and breaks all the way, going all the way up. Right? So the two strands of DNA aren't covalently bonded together. They're held together through hydrogen bonds. And obviously this is a critical, DNA and RNA are critical pieces of biology, and replication of DNA and RNA occurs because we can take those two base pairs, or those two strands apart, and match up the base pairs and replicate them. Right? So this is the important part, or this is the introduction to intermolecular forces. Let's go back now. So at the beginning we said we had this table. This table, or this flowchart, and the flowchart tells us what intermolecular forces are active. So if I don't have polar molecules, the only forces that hold nonpolar things together are dispersion forces. If I have polar molecules, the next question is, do the molecules contain any oxygen-hydrogen bonds or nitrogen-hydrogen bonds? If they don't, we have dipole-dipole forces and dispersion forces that hold those molecules together, or that pull those molecules together. And then if we do have molecules that contain OH bonds or NH bonds, we now have hydrogen bonding occurring. And in those molecules, we have all three forces working to hold those molecules together. Okay. Typically, we consider hydrogen bonding as the strongest of the intermolecular forces by far. Dipole forces are second, and dispersion forces are third.